You have a random variable x, which is normally distributed with its mean mu and its variance sigma squared. Now there is another random variable. Let's call this x1, so the other one is x0. It's also normally distributed, but with a different mu and a different sigma squared. Let's create a joint random vector consisting of these two random variables. Then our plot are just slices from a 2D probability density function. But can they also interact with each other? Welcome to this video where we'll introduce the multivariate normal distribution. Hi, the agenda for this video is that we will first give an intuition for the multivariate normal. We will look at visualizations and some aspects that are relevant for computing the multivariate normal. In the end, we will then look at TensorFlow Probability. Let us quickly recall what we had in the intro. So we had two random variables, an x0 and an x1. Both are normally distributed, and I drawn their probability density function over their respective axes. What I haven't drawn here is that these two jointly form a two-dimensional bell shape, and we will soon see how this looks like. Let us quickly note down what we have to save for both of the random variables. So let's call this what to save. We have the random variable x0 and we have the random variable x1. And the parameters of x0 are the mean, which is a mu x0, and the variance, or you can also call it the standard deviation, which would be sigma squared x0. And for the random variable x1, we have to save the same, which would be an mu x1 and a variance sigma squared x1. But if we just save these two values per random variable, then we would get something that I also drawn in here. We have a normal distribution in each of the axes here, but this is not interacting with each other. And by interacting with each other, I mean that in the three-dimensional space, we can have a normal distribution which is not axis aligned, so it is some sort of like rotated around this third axis. You maybe call it the z-axis. So we need another parameter for the multivariate normal in order to encode this. This joint parameter is called the covariance, and it is for the, well, interaction. Let's put this in quotation marks. So the covariance, and the covariance will be denoted as a sigma index x0 and x1, denoting that it is the interaction between the x0 random variable and the x1 random variable. And as said, it can be imagined as the rotation around the third axis, which is of course a little bit limited to our two-dimensional scenario, but just think of it as something that is rotated. In the intro, we already introduced the random vector, and the random vector was the collection of these two random variables. So in our two-dimensional case, it was an x, which consists of an x0 and an x1, and it is a two-dimensional vector. It can take any value from the two-dimensional space. The interesting question now is how we can define a probability density function over this two-dimensional space, and that's also where the multivariate normal really shines. So let's look at the probability density function. And for this, let us quickly recall the univariate case, or the case for a scalar valued normal or Gaussian distribution, and there we had a p of x given as the normal distribution over x under a parameter mu and a parameter sigma squared for the variance, and then we had 1 over the square root of sigma squared 2 pi times the exponential of -1 over 2 sigma squared, and then in brackets x minus mu squared. And recall, this factor was just a normalization, so let's ignore it at first and look at this term here. So now we have to consider the probability density function of our random vector, so underscore for the vector. It is proportional to, because let us first ignore the normalization constant. And surely if we want to have a normal, we kind of need this exponential minus, because this is what essentially creates our bell shape. And we also need some sort of a square here. Let us try to generalize this. Since we now have an x vector instead of an x, we also have a mu vector instead of a mu. So maybe just take the difference of those two and then raise it to the power of 2. Does this work? But look at it. A vector minus a vector is another vector. And you can't square a vector. So we need to find something that is the analogon of what we have here. And the generalization of this quadratic equation that we have in the exponential is the quadratic form. For this, we have to use the difference from the actual x vector to the mu vector and then transpose it. And then there will be something in here and then multiply it with itself, and this will then be the scalar product, because vector transpose vector will yield a scalar. But then we have the 1/2 sigma squared, and the sigma squared encoded the variance, or in other words, the spread of the normal distribution. But now we have three parameters. So we have the spread of the first variable, we have the spread of the second variable, and we have the interaction of these two variables, or the joint spread, you can call it like this. So we have three parameters. How can we do this? Like three scalars. And the idea is to build a symmetric matrix that we will call capital sigma, and it is a matrix. And since here we would divide by it, we have to use its inverse. And we also keep the 1/2 here in order to get a similar form as in the univariate case. So let us note this down. What we have here, we have the mu vector, so a mean or a mu vector. This one consists of the mu x0 and the mu x1, so the mu for each of the corresponding variables. And we have the sigma squared, which is the covariance, or you can also call it the capital sigma matrix. And it is given as sigma matrix is, in our two-dimensional case, the sigma squared x0 and the sigma squared x1. So the one that we also had in the two univariate cases. But then we also save the interactions and we put them on the off-diagonal elements. So we put them here, a sigma x0 x1 and a sigma x1 x0. And right now we see, well, these are different, but actually they have to be the same because this matrix has to be symmetric. So we can also call this here an x0 and an x1. So let me keep the circle here and then closing matrix. And also let us note this down, this one here and this one. These are the covariances. And we call it the covariance matrix because it consists of the covariances and the variances. Now let's look at how this is plotted in 2 dimensions. So here I have the surface plot and we have the x, which will be our x0, and we have the y, which will be our x1, and we have the z, which is the probability of the vector. And here, take care, it goes in this direction, this is a little confusing. And we see the surface is yielding the probability density at each spot. And we can see that approximately here is our mu vector. So maybe it's something like, well, it should be a 2 minus 2. So that's where our distribution is centered around. That's where the peak is for the highest probability density. And then we see one more thing. And if you look at the isolines here, these are ellipsoids. They are no longer circles. And this is because we have a higher variance in x0 than in x1. So we have higher variance. And that causes that our isolines or our contour lines are ellipsoids. But we can also see another thing, which is similar to the intro, where we also had different variances on the random variables, and that is that our distribution is still axis aligned. So it is still axis aligned, and this would mean that our covariances are 0. So the covariances are 0. In our case, we only have one covariance, but this is 0. But if it wasn't 0, then we would turn around the mean, and then our distribution would have isolines that are ellipsoids in the general R2 space and not necessarily axis aligned with the x0 axis and the xy axis. And surely we looked at two-dimensional examples, but the great thing about the multivariate normal is that it generalizes to, well, let's call the dimension D. It generalizes to 3 dimensions, 4 dimensions, 100 dimensions, 50,000 dimensions, and so on and so forth. And if you see applications of the multivariate normal, it's really common that it gets into extremely high dimensions because you can do really, really handy things with it. And it's of great use for a lot of topics in statistics and machine learning. Let us now introduce the normalization constant. So because earlier we looked at the probability density function, and for it we said that we just look at the proportional first. Now let's look at the proper probability density function. So we have a p of x, and recall for the exponential term we had e to the minus 1/2, then vector x minus vector mu in brackets transpose, then inverse of our covariance matrix, and then x minus mu again. And for the normalization, recall for the univariate case we had 1 over the square root of sigma squared 2 pi. And we should keep the 2 pi. If you watch the video on the derivation for the normalization constant, you see that this is kind of natural, but we have to raise it to the power of d, because we are now in higher dimensions, and then this constant appears multiple times, so raised to the power of d. But then we also have the sigma squared. How can we express a sigma squared with our covariance matrix now? And the idea is to have the determinant of this sigma matrix, and this will then be our normalization constant for the probability density function, and now it adheres to the property that it integrates to 1. So let us also note down the d here, which is just the number of dimensions, and in our case we were in 2 dimensions, so d would be 2. And we will define the just introduced normalized multivariate normal with an capital N over vector x given a vector mu and a matrix capital sigma. Similar to other distributions and also the univariate normal, the parameters of the normal have to adhere to certain requirements. So let's call this the requirements. And the first parameter is the mu vector, and it is from the Rd, because in general it's from a d-dimensional space, and it can take any value, there is no restriction on the mu. But recall, in the univariate case, we had that sigma and sigma squared have to be strictly greater than 0, because they define the spread around the mu, and so they have to be a non-negative number, right? How can we encode this in multi-dimensions? Can we just say, so in multivariate, can we just say that the sigma matrix has to be greater than 0? But what does this mean? Does this mean component-wise? No, actually if you look at matrices and you see equal signs, then this refers to definiteness. The greater than sign can be understood as symmetric. Well, this makes sense, we looked at it earlier, that has to be symmetric, but more importantly, positive definite. And that's the crucial part. If your matrix is not positive definite, then you don't have a multivariate normal. And usually if you're introduced to positive definiteness, you learn some criteria when the matrix is positive definite. I would recommend you to forget about this, because from a computational point of view, they are not relevant. The really important aspect is how to check for positive definiteness of a matrix is because there is the theorem that a matrix is positive definite if and only if there is a Cholesky decomposition. And the Cholesky decomposition tells us that symmetric positive definite matrices can be decomposed into a lower triangular matrix and times this lower triangular matrix transpose, which will be an upper triangular matrix. So this is a lower triangular matrix. Most of the software packages that you will use for probability theory always contain algorithms to compute this Cholesky decomposition, and if this algorithm fails, then the matrix is not symmetric positive definite. And of course you can easily check for symmetry, but the second one is usually the one that is a little more complicated. But Cholesky decomposition is not just a way to define the positive definiteness for a matrix, but to also compute its inverse. So it's not just used for the check, but also for the fact that, recall, because in our format we had the inverse of the matrix, it is also used to compute that one. So we have it is also relevant for the inverse. And of course, if you are a subscriber to this channel, then you might have seen earlier videos where I say that never compute the inverse. This is just a concept, the inverse, and actually what you use is substitution solving, which mimics inverse matrix computation. It's not relevant for understanding, but just never compute the inverse explicitly, always use decomposition of matrices. But with this in mind, we can also ask us, what is about the precision? So call this what is about the precision. In the univariate case, the precision was the inverse of the variance. So recall, in the univariate case, we could also parameterize a normal over x with a mu and a tau. And we write this inverse in order to denote that it's mimicking the variance. And then our functional form is given as the square root of tau over 2 pi times the exponential of minus tau half times x minus mu in brackets squared. And tau was defined as the inverse of sigma squared. And here we actually do the same for the multivariate case, where we define another matrix. So in the multivariate case, we define another matrix which we call capital lambda, and it is the inverse of the covariance matrix. As I said, never compute the inverse explicitly. This is just handy for derivations. So this is useful for derivations, and maybe if you have small matrices of the size 3 by 3, 2 by 2 or something, then you can also calculate it explicitly. But in general, please don't do matrix inversion. This is just a handy thing that is required for some Bayesian analysis. So this is for Bayesian analyses, for instance, calculating posteriors and so on and so forth. And if we then look at our definition of the normal, then we have p of x is given as the normal or the multivariate normal over x under the parameter mu vector and lambda inverse. And by this we indicate that lambda inverse is mimicking the covariance matrix. Let us first look at the exponential term, and here we have minus 1/2 in brackets x minus mu vector transpose, and then we have the lambda here, and then times x minus mu in brackets. And here we also see the advantage of using the lambda, because we no longer have the inverse in the exponential. And the normalization constant also becomes simpler, because then the determinant is in the numerator, and we divide by 2 pi in brackets raised to the power of d. Now let's look at some interactive visualizations for the multivariate normal. I have a web plot here, and the link to it is also put in the video description. And here we see again our multivariate normal in the form that we also wrote down here. And on the right, we see the current parameters for the mu vector and for the covariance matrix. And on the left, we have 5 sliders, because we have 5 parameters in 2D, which are the x position, the y position of the mean, and the variance in x, variance in y, and the covariance, which is the off-diagonal element. And we only need one slider, of course, because it is the same for the upper diagonal and the lower diagonal element. And the default values here are variance 1 and 1, so the standard normal, but with a center at x is 2 and y is 1. So you see the peak of the distribution is here, the highest value. We see the contour lines, and they are circles because it is radially symmetric. And we can shift the multivariate normal around by, for instance, moving it more towards the left, and then we see it is there, and even further to the left, then it is there, and the plot updates. That's really cool. And we see the mu is not affecting the contour lines, it's just affecting their positions. We can do the same thing as we had in our introduction, where we had a different variance in x than in y. For instance, let us increase the variance to, well, let's say maybe 1.9 or 2. And then we see our contour lines are becoming ellipsoids and are no longer circles, because we have a far higher variance in x than in y. And we can also maybe put this into extremes, make this a 3 and make the y a little smaller. I think you see it, then it gets really narrow and it's more towards in the x direction. But so far we haven't talked about covariance yet. So let us introduce a little bit of covariance. And the covariance, in contrast to the variance, is not limited to be strictly positive. It can also be negative, and here we see it can also be 0, because then we have our axis-aligned multivariate normal. So let's introduce a little bit of covariance, and we see the covariance rotates us around the z-axis. Positive covariance means that we rotate mathematically positive, which would be counterclockwise. Negative covariance would mean we rotate mathematically negative, which would be clockwise. And we can also put in more covariance, like this, and maybe also reduce our variance a little bit in order to make our plot a little bit more narrow, and then increase the covariance even further. And then, oh, the covariance matrix is no longer symmetrically positive definite. We can also check on this because we have really high off-diagonal terms. Usually symmetric positive definiteness is also correlated to diagonal dominance. So if the diagonal is way greater than the off-diagonal elements, and here it is not the case. Well, it's still symmetric, but it's not positive definite anymore, and so we don't have a normal. And then we have to reduce the covariance, and that makes also sense because the covariance is just telling us by how far we want to rotate. And the rotation is limited to a little bit. We can't just rotate 3 times around the axis and so on and so forth. And feel free to play around with it a little bit. We can also go in a negative direction, and we see that in this case it will also be not positive definite anymore. For TensorFlow probability, let us first define the parameters, and we have to define a mu vector, which will be containing 2 components. For instance, let us center our distribution around 5.0 and 1.0. Now we have to define a covariance matrix. So this will be a matrix. So we have to first define the first row. And let's, for instance, have a variance of 3.0 in X and have a covariance between those two of 0.5. And then we have the 0.5 again, because otherwise our covariance matrix wouldn't be symmetric. And lastly, a variance in Y. For instance, let this be 1.5. Then we close this down. We can look at the covariance matrix and see this is what we just defined. Then let us perform the Cholesky decomposition. With this, we will also figure out that our matrix is symmetric positive definite. For this, we do TF, so TensorFlow.linalg for linear algebra, and then Cholesky, and apply it to our covariance matrix. And we see it didn't raise an error. If it would raise an error, then it could be, and most certainly that's the reason that our matrix is not symmetric positive definite. And we can look at L, and we see it is a lower diagonal matrix, so it does not have any upper diagonal elements anymore. And this is what we will also be using in order to define our multivariate normal. But before we go there, let us first check how the Cholesky decomposition raises an error. And for this, we do TF.linalg for linear algebra, and then Cholesky. For this, let us take the matrix as, for instance, 0.5 in the variance in X, then 1.8 in the covariance. So there's a lot of mass on the off-diagonal elements. And then for the second row, we will do 1.2 and 1.4. And you see, first, the matrix is not symmetric. 1.8 is unequal to 1.2. So if we execute this, then we see Cholesky decomposition was not successful, so the input might not be valid. And even if we fix it, so for instance put it to 0.8, and now we have a symmetric matrix, it also fails because it is not symmetric positive definite. So recall the probably best check for symmetric positive definiteness is whether a Cholesky decomposition is successful or not. But with this checking in mind, let's return to our L, so the lower diagonal element. And I want to emphasize one point. In the one-dimensional case, we had the normal defined either by the standard deviation or by the variance. And now we have a covariance, and a covariance is something like the variance. And now you could ask yourself, can't I just take the square root of the covariance to get something like a co-standard deviation? And indeed you can. Well, it's not technically the square root, but that is what this L is. So L, or also we call it the Cholesky factor, is the square root of the covariance matrix. Then it also makes sense that we will now define our multivariate normal by the help of L. Because in TensorFlow probability, we always defined it with the standard deviation instead of the variance. But since these are always interchangeably, and since we have to require a symmetric positive definite matrix, we can always define it in either of the two. Okay, long story short, let us go to the multivariate normal. I call this MVN. And this will be a TensorFlow probability distributions, and then multivariate normal. And there are a lot of options for multivariate normals. I will cover all of them in a separate video, but we will use the form that's called tri-L, which stands for triangular lower diagonal. So we put in first the location, which is our mu vector, and we put in the scale trill, which is the scale lower triangular matrix that we just computed with the Cholesky decomposition. And then we have a multivariate normal, and if we look at it, we see it has no badge shape, that's great, but it has an event shape of 2 because it is a 2-dimensional random variable now. and we can sample this distribution, for instance. Let's sample it 10 times, and then we get 10 values, and they are now distributed according to the mu and the covariance matrix that we defined earlier. And similar to other distributions, we can also query, for instance, the mode. And we see the mode is of course equal to the mu, because the mode is the mean of the distribution for a multivariate normal. And we can also query the probability for certain outcomes. For instance, let's put a value that is probably more likely, something like 4 and 0.8. And for this we get 0.065, so 6.5%. But if we query the probability of an event that is not that probable, so for instance minus 3.0 and 15.0, then we get 0, because that is even underflowing our floating point value precision. So we have to go to log probability, and then we get minus 96, highly unlikely. And if we check the log probability of the original one, we have a more likely event. One last point before we finish the video is that when we defined the multivariate normal, we did the Cholesky decomposition prior to it, but you can also do it within here just by calling tf.linalg.cholesky and then apply it to the covariance matrix, closing brackets, and this works the same way. Thanks for watching this video. If you enjoyed it, then please consider liking and subscribing. I would extremely appreciate this. Here you will now find similar videos, and there's more cool content coming in the future. For this, I hope to see you next time.